Nice to be in orbit.
So this is some technology stuff. This is a 1/4 micron transistor. This is in comparison. It's an Fmax chart. Fmax is the maximum power you can get out of a transistor, not the maximum frequency at which it will conduct current. So F sub t is basically the length of time it takes for an electron to get across a transistor. That's essentially what F sub t is. It's channel length and it's mobility. This technology won't help that. It's just that simple. But Fmax is how much power you get out versus how much power do you put in. When has that got a unity ratio? And in all those bulk devices and things with a whole bunch of capacitors to ground, guess where most of the power goes? That's right. At 30 gigahertz, it goes right through that capacitor into the substrate and gets dissipated. So you get way less power out than you put in. If you're sitting on Sapphire and you put power into this, let's say the source, or it's coming out the drain, it sure ain't going through the Sapphire because it can't conduct and there's no capacitor there. So that means all the power has to come out. So the Fmax of this transistor is approximately the same as Fmax of a pHEMT, which also has a semi-insulating substrate. So while the F sub t's are the same as bulk, the Fmaxes are typically 3 to 5 times higher. That changes how you design transistors and how you design circuits. You have to design circuits around Fmax rather than F sub t. If you look at most circuit designers who are used to bipolars, bipolars have wonderful current gains, so they think in terms of F sub t. Of course they do. Fmax is no better on a bipolar than the F sub t, usually less. So that architected thinking differently, it does determine what products you make, etc. But it's an interesting factor that the Fmax of our 1/4 micron transistors were approximately equal to then like 70 nanometer transistors coming out of IBM. So we knew we had a big advantage. Remember, a 1/4 micron fab, mask sets are $15,000. A 70 nanometer fab, mask sets are $1 million. And you get to spin them 2 or 3 times in RF to get things right. And there aren't that many fabs that'll do it for you. So it's, you know, it's actually nice to be able to use old technology and old facilities, fully depreciated, instead of bleeding edge state of the art that's incredibly expensive and maybe not even stable. So we realized we had linearity, we had Fmax, and we got to use old fabs. Seemed like we could do something. Here's some data. This is one of those early mixers where we were single IP3s up in the high 30s at the time. That was easily the best single FET quad mixer available. Isolation, Sapphire is magnificent. To this day, Dan, correct me if I'm wrong, I believe we're the only company that can meet the FCC Type 15 spec for a TV that has a cable input and an FM radio or an antenna input. Because you have to have that, a huge amount of isolation, 80 dB, so that the cable signal doesn't go out your antenna and give it to your neighbor. So most TVs, they either have, in fact, almost all of them have our chip in it for that reason. They don't have to get waivers. So that Sapphire isolation is just magnificent. Then we started asking ourselves, what else can we do with this? And basically what we realized is because our transistors were sitting on Sapphire, they're completely independent. You could stack them up and you could put RF on a stack. And it not only will divide amongst those transistors, just like as if you had soldered them together on a PC board, they'll divide perfectly. Why? Because the nearest parasitic is, it's in Chandler, it's in Escondido somewhere compared to where we are. There's virtually no parasitic capacitance to worry about, so the voltage division was perfect. So we started working on this back in the early 2000s. In fact, maybe a little before that. And basically it shows if you have 1, 2, 3, 4, 5, 6, 7, 8 transistors, they all can handle, let's just say 3 volts because I can do the math. 8 times 3 is 24 volts. 1 watt in 50 ohms is, I've forgotten, 18 volts or something like that. So you can handle a watt with a bunch of 3-volt transistors. So with that realization and developing this, we realized we can not only handle power, we can do it incredibly linearly. But when you hit these stacks with high power, when that voltage goes negative, it starts turning on the bottom transistor. So you have to have some negative voltages in there to hold things off at high power. So we had to come up with spur-free charge pumps. Those of you know who Giora Goldberg is, founder of Cytec, he used to work for us. When we said we were going to do this, and we're going to put the charge pump, and we're going to put the level shifters, and we're going to put all the digital logic, and we're going to handle, at that time, GSM levels of power, which is 4 watts, 2 watts into 50 ohms. No cell phone works in 50 ohms. The antennas suck. So you add a VisWire of 8. We just said, screw it, we'll just go to VisWire of infinity, which doubles the voltage, which quadruples the power. So a 2-watt switch we designed for 8 watts. That way, VisWire, schmizwire, we didn't care. Why? Put on more transistors. They're free. Almost. So with this, we could take what at the time was a 35 square millimeter switch module for a GSM phone, and we took it and reduced it to a single chip, and by flip chipping that onto a ceramic substrate, we reduced 35 square millimeters to 7.5, 8.5, something like that. It was a 5x reduction in the area. It reduced the component cost. They didn't have to, because we had the control logic, they didn't have to buy a control chip. They didn't have, we took care of the spurs, the spurs in the charge pump. That's what Giora said you'll never succeed at. You'll never get the spurs out. They'll show up in the radios. Thanks, Giora. The wrist protects you. We found a way. Dan and his team found a way to get rid of all these problems. And today, literally, we have about 1/3 to 1/2 of all of the RF switches in cell phones. And today we have 100% of all the LTE advanced switches in cell phones, because we've come out with now our 10th generation of technology that improves all the performance metrics by at least one entire generation. So this was a very clever development. It came from the inner insulating substrate, and it allowed us to deliver linearity and power. I mentioned public safety radio. We actually make a switch for them. No, we don't make a switch for them, but we actually make a 30-watt switch. You can do the math. 30 watts, if you got to have at least 10 transistors. Oops, there's that factor of 4, so we stack. Some of our chips have 15, 18, 20. You just keep stacking, you can handle more power. And this is an example of what it looks like. We actually have gone in, done these simulations, and this voltage division is literally perfect, which means there's no compression, there's no more voltage here than down here. Every transistor is operating in the same place, so it behaves linearly.